my name is Paczos, and at the beginning, I would like to say thank you to the organizers for organizing this event and for letting me give a talk which will be on the Hawking radiation as perceived by detectors following a superposition of trajectories. And this is based on the research that I'm doing in collaboration with Luis Barbado. And in a way, this is a follow-up of the research done by Luis on the Unruh effect in superposition of accelerations. He has a poster on that, so check it out. Let me begin by bringing up probably the simplest setting that we consider when we investigate Hawking radiation. In this setup, we have a Schwarzschild black hole, which fixes the background, a real massless scalar field, which lives on this background, and a detector, which we put on a static trajectory in the vicinity of the black hole, and we let it interact with the field. We can think of the detector as a multi-level system. And if we choose appropriately the state of the field, we will find out that with some probability, the detector will get excited, testifying to the presence of some radiation. In our problem, we modify this setup slightly by considering many static trajectories and by letting the detector follow a superposition of these trajectories. So we have in our problem 3 degrees of freedom. To each of them, we associate a Hilbert space. We will have internal energy levels of the detector, static trajectories, and the states of the field. We will assume that the interaction between the detector and the field is given by the standard monopole interaction Hamiltonian. And we will fix the initial state of the system to be the ground state of the detector, some state of the field, which we will take either Unruh or Hartle-Hawking, and the superposition of trajectories with some coefficients an. So we fix the initial state and we let things happen. We let the field interact with the detector. And after infinitely long time, we check what is the final state of the system, but disregarding the quantum field. So what do we get? Here in the first line, we have just the initial state of the system without the field. So this corresponds to the situation in which there was no excitation, no interaction between the field and the detector. The second thing is the sum over the diagonal terms, in which corresponds to the Hawking radiation effect for each trajectory separately, combined in an incoherent way. So when we consider a single trajectory, this will reproduce the standard Hawking radiation effect. And finally, in the last line, we have the true novelty of our approach. So this is the sum over the non-diagonal terms, which corresponds to the coherences left in the final state of the system, of the detector, after the interaction. And in particular, we will be focused on the coefficient lambda, which we will treat as a measure of the coherence. We managed to find out the exact formula for the coefficient lambda. I will not bring it up here since it is quite complicated. But what we found out is that lambda is equal to 0. So there is no coherence after the interaction, unless the following condition is satisfied. Here, alpha n and alpha m correspond to the gravitational time dilation factors on the trajectories n and m respectively. And this condition means that the energy of the excitation as perceived by any static observer must be the same on the trajectory n and on the trajectory m. Okay, but why do we care about the coherences in the final state of the detector? Well, the coherence in the final state of the detector means that the detector did not get fully entangled with the field throughout the interaction. This, on the other hand, means that two states of the field left after the excitation of the detector on the trajectory n and on the trajectory m, that these two states of the field are not fully distinguishable. And what could be the reason of such non-distinguishability? Well, maybe this occurs because the detector on both trajectories could have swallowed the same particle. So the coherences in the final state of the detector provide us a kind of notion of spatial localizations of the particles in the field. Okay, so if we agree that coherences are worth our attention, we can think about the visualization. So we fix the ratio of the energy divided by the gravitational time dilation factor, and then the coefficient, this coefficient lambda becomes a function of just the trajectories. To be more precise, of the radial distance of trajectory m, radial distance of the trajectory m, and the angle between these two trajectories. So in particular, we can fix one of these trajectories. We will fix the trajectory m and variate the radial distance of the trajectory n and the angle between these trajectories, which will allow us to make a 3D plot of this measure of coherence of lambda. And this is what we get when we consider Hartle-Hawking state and the ratio equal to 1. So we see that we have a single peak in the middle. This corresponds to Rn equal to Rm and theta equal to 0, which means that the trajectories n and m are in fact exactly the same trajectory. So it's not very surprising that we have a maximal coherence here. The surprising fact is that the second largest coherence appears on the antipodes. So for theta equal to plus minus pi. Okay, and we can compare this with results for other values of this ratio. We see that basically the largest is the larger is this ratio, the more oscillations we have on the plot. And we can also take a look on what we get for the Unruh state. Well, now again we have a single maximum for coinciding trajectories, and the second largest coherence is again on the antipodes, but now we don't have a rapid decay for growing Rn, but rather a slow one. Slowly, the lambda decays slowly when we increase the radial distance. And comparing it with other ratios, we see basically the same thing. So the larger is the ratio, the more oscillations we have. Okay, that's it. If it comes to the results, we can also consider some further questions to be addressed. First of all, we considered static trajectories, but one can also take a look on other kinds of trajectories. For example, we think that circular geodesic trajectories shouldn't be much harder to treat than static ones. One can also consider other kinds of spacetimes. So Lewis considered flat spacetime and Unruh effect. We considered Schwarzschild spacetime, but there are many more to consider. And finally, we can try to interpret our results in terms of quantum reference frames. In the formalism of quantum reference frames, we can consider a situation in which we have a classical observer and a quantum system which is in a superposition of locations. And this formalism tells us that we can transform to the reference frame of this quantum system, in which the classical observer will be in superposition and the quantum system will follow a well-defined trajectory. So in this language, our problem should be analogous to the situation in which the detector follows a well-defined trajectory and the black hole is in the superposition of locations. That's it. Thank you for the attention.
Yes.
Hi, thanks for the talk. It's something that I didn't understand. You mentioned, can you go back to the state of the detector, the row after the interaction? You have it at one of the first slides. You mentioned, you mentioned something that you let it interact for a long time, infinite time, you said.
Yes. Yes.
What kind of calculation is this, and what is t? Is t the?
T is okay. Okay. So here in the interaction, we have a function,
Right,
which switches.
So it's not interacting for infinite times. What you mean is that you have a switching function, right?
Yes,
that
yes.
is non-negligible for a finite amount of time t, right?
Yes.
Okay,
Right.
because otherwise I was about to tell you, but then your state is not well defined. Okay.
Yes.
So is there another quick question there?
Yeah, just a big quick curiosity. Have you ever calculated the entropy of the final state of the detector?
We didn't. We didn't calculate.
Okay, it will be interesting.
Okay.